It's Soham from Team 16197, and today I'm going to give you guys a presentation on effective prototyping for a successful season. So what is prototyping? So prototyping is a way for you to develop an early sample or model of a product built to test a concept or process. So this means it's not your final design, it's something that you'll be using to test your final product. So a prototype can be a software prototype, a hardware prototype, electronics, and there are also prototypes in other fields. But today we're going to be focusing on hardware prototypes because teams have a lot of difficulty with doing these effectively. A prototype also is something to help us evaluate new designs for feasibility and success and allow you to plan out the rest of your season. So why should you prototype? So prototyping will save you time and money down the line because you're able to test stuff out with cheap materials and not risk spending a lot of money on expensive materials and building something and 2 months in finding out it doesn't work. It also allows you to test out multiple designs in real environments so you don't show up to competition with a robot that falls apart. And it allows you to try different things so you may be able to try different types of mechanisms that you wouldn't have time to fully flesh out. It also engages new students because with the prototype almost anyone can participate. You don't really need really good hardware skills or really good software skills to put an idea out there and test it out. And it really helps you learn what's hard and what's easy. This is one of the most crucial parts of prototyping because often a lot of teams assume something is easy and then later find out it's hard. So one example of this is in Skystone this year. A lot of teams used wheeled intakes to intake stones during autonomous, and initially everyone was using wheeled intakes to suck in these cubes, and they thought, oh, it's okay, I can predict where these cubes are going to fly around and then get the next cube on my next autonomous cycle. But soon they found out that using a claw was a lot better, and it allowed teams to do a lot better because with the claw they realized it wasn't affecting the other stones as much. So prototyping really helps you learn things you don't expect or aren't able to understand from the game video or the manual. So what questions does prototyping help you answer before heading into the season? So as I said before, it really helps you understand if your design will work in an environment similar to the one you're going to be experiencing at competition. And it also tells you what issues you need to solve before you put more work into something. As I said before, you don't want to spend a lot of time working on something and then finding out it doesn't work after working really hard on it. So you want to iron out as many issues as you can early on. It'll also tell you what difficulties you'll face building and manufacturing something, because if you're not able to build a simple prototype to demonstrate the concepts, you may run into a lot of difficulties later on actually building the final design. So what are some disadvantages to prototyping? I've talked a lot about advantages, but with everything there's pros and cons. So obviously the biggest disadvantage to prototyping is it'll cost you extra time and money, but in the end it'll probably save you time and money. You might spend some money on prototypes, and you might spend the first 1 or 2 weeks or maybe even more of your season, depending how it goes, prototyping. And you might think this is a big waste of time because you're not actually building a robot that you'll go to competition with, but then you'll realize the benefits of prototyping when you're saving time because you have a solid design before going into your competition robot, and you won't waste money on expensive parts that don't end up working. It also uses up materials, so depending on how you prototype, you might use up consumable materials like wood and things, but we're going to be talking about building strategies to reduce the waste later. There are also mistakes during prototyping can translate into choosing a bad design. So if you make a mistake during prototyping and think your prototype is good, in the end you can end up with a bad design even later than if you had just built that design initially. But this can be solved by just doing some good prototyping and following the practices I'm going to lay out during this presentation. So how should you start with your season and prototyping? So first you need to set out a plan. You need to figure out when your first competition is. This year there's a lot of variability. I know Ms. Francis and Mr. Edelman sent out a form requesting people to indicate when they would like to compete and how many competitions teams would go into. So we don't really know about that, but at the earliest, competitions were the second or first week of November, but a lot of teams wouldn't show up until December, maybe January or even February. So really this when is your first competition decision depends on how your robot is going and how confident you are in your team's abilities. In addition, it can depend on how much time you can spend at school or at home building the robot. and it also depends on how much money you're able to spend on multiple competitions, where you can push for a really ambitious thing in your first comp and fail, and then show up to a second competition after refining your initial plan and having that be successful. So this is really going to depend on your team and the season. With COVID-19, we have a lot of new factors that play into this, so you're going to have to decide this for yourself as a team. In addition, it's the same thing. How much time can members spend per week? This year, it's really different. A lot of schools can't meet at all, or maybe one or two people can meet in the robotics room. A lot of home teams, parents aren't letting students go over to each other's houses and meet. So you really want to figure out how much time you can spend per week early on, so you have a plan going on how much time you can spend. And then you need to figure out at what point you guys need to go from a prototype to a full robot, so you have something by competition. You can't obviously extend your prototyping season or prototyping time out into the first competition. You really have to set a hard deadline, and at that deadline you're going to say, okay, let's see what we have right now, let's pick the best solution, and let's really get that working as best we can, so we actually have something to present during competition. You also have to figure out how much money and time you're willing to use for prototyping. As I said before, I talked about the time constraint, but there's a money constraint. You may be able to buy a bunch of new parts for prototyping, or you may not have any new parts for prototyping. So you really have to figure out how much time you're willing to put into this and how much time you think it'll change. And you also want to figure out what your standards of evaluation are for your prototypes. So I'm going to talk about this more a little later, but this is going to be really important. So these are some tips for working virtually that our team came up with. So one great thing about Zoom or Discord or other services is you can put students into breakout rooms, or robotics team members into breakout rooms. So with robotics, you often don't want everyone working on the same thing at the exact same time, and you don't want people working together on brainstorming at the exact same time to avoid having like one idea arise when you could have multiple students come up with 5 individual ideas or more. So you really want to break out students individually when needed to have them brainstorm in small groups or brainstorm on their own. A coach may also want to distribute game elements to students, because students can work at home with materials they have and try to figure out things that work. An example of this would be this year we had the Skystone stones, and we wanted to grip them with a gripper. So our team, we each kind of went home and thought about different materials that could work on the stones. I found a material in some Lego silicone thing I had that stuck or gripped the stones really well, so we ended up using that. But one thing that might have worked well was the silicone coasters I had that were really rubbery and kind of grippy or sticky with the cubes, so we might have ended up cutting up one of those. So by distributing these game elements to students at home, they can work at home and try to figure things out on their own in the off time. So you also may need to designate a few volunteers with access to tools to build the prototypes with the team watching. And one really important thing about this is that you want to keep the team engaged throughout the prototyping process. You don't just want those volunteers to work at home or work in your robot shop by themselves. You want everyone involved in the prototyping process to make sure the team sticks together, which is especially difficult now that we're not doing in-person meetings. And communication is the #1 priority. I would recommend not just communicating over email. You probably want to use Slack or Discord or something you can create organization and communicate goals and timelines and just chat within your team. Because one of the best ways to come up with ideas is just having chatting over ideas when you're not really stressed about having to come up with an idea on the spot. So let's start with the day or week of kickoff. Of course, this can go on longer depending on how much time your team has. For our team, this generally takes the first 1 or 2 days. I know at our high school, when I did FTC as part of Cupertino High School, it took a week or 2. So this really also depends on your team. So you want to determine all the game objectives. So a lot of teams start prototyping after watching the game video at kickoff, but this isn't the right approach. You really want students to spend maybe an hour, maybe 2 hours, depending on how fast they can reading the manual. So there's this motto in engineering, RTFM, which stands for read the manual, and I'll let you guess what the F stands for. But this is just kind of out of frustration when people come up with prototypes or designs and propose them to the team, and they may not work, and they may not follow the rules. When I say they may not work in the context of the competition, as in they may not achieve the goals that you set out, or they may not follow the rules, and this is a really big waste of time for the team. So an example of this maybe in Skystone, a lot of teams kind of predicted it was a stacking game well before the season. So in FRC, there's this Recycle Rush challenge where teams decided to stack a stone, and stack a stone on top of another stone, and stack a stone on top of another stone. And then in the end, when the game manual came out, we found out that it just wasn't allowed, right? You could only grab one stone at a time, so you couldn't do this stacking method that teams really wanted to do. So then after that, you really have to decide on the wants of your team. You need to figure out what you want your robot to do, and you really need numbers. You need to quantify these as best you can in solid numbers. So when you go into prototyping, you have goals you can achieve. Instead of saying, I want to raise blocks, you should say, I want to raise blocks at least 6 high. Instead of saying, I want to in blocks, I want to touch it and own it within 1 second. Instead of saying, I want to have a successful autonomous, say, I want to do 1 stone during autonomous. And then these can obviously change throughout the season. You may say, for our first competition, we want 6 high. By our second competition, we want 10 high. And make sure not to design right now. This is just listing out the criteria of your design. You don't want to start designing now and limit your flexibility later. And you don't want your design to influence your strategy. So this is, deciding your wants is basically your game strategy. What do you think you can accomplish, and what points will you go for? So then you want to start brainstorming. Hey guys, sorry about this. My video cut out and I didn't notice it was frozen. I wasn't able to get it working, so I'm just going to continue without the video up here if you were noticing a change. So when brainstorming, you really want to start by looking at old games. These can include FTC, FRC, and VEX games. Don't just limit yourself with FTC. So a motto you're going to be hearing a lot in first is called steal from the best, invent the rest. What this means is you can look at old designs or old teams that have done really, really well, copy their designs, and then work on fine-tuning those to specify the game or changing things up. So one FRC team, I remember they highlighted what they did. They realized the game element was basically the same as a game element a couple of years ago, so they found a really good robot from that previous year. They then projected the robot onto a board, and then they stuck a piece of metal onto the board, cut out that mechanism, tracing it out, and then they slapped that on the robot, and it was successful for the season. So you really want to use this philosophy. In engineering, it's not really stealing ideas, it's really building off others. And during this stage, you also need to know that no idea is a bad idea. Everyone should have the freedom to bring an idea to the table, no matter how bad it is or how bad you think it is, because a lot of ideas can get lost if someone shuts them down or is overly critical at this stage. So you really want to come up with a bunch of ideas. And you also want multiple ideas per criteria specifically. So if you have, if you define one of your wants, if you decide one of these wants is a shooter, you want to say, maybe let's build catapult shooter, or wheel shooter, or a flicker shooter, or a piston shooter, or something like that, to really have a bunch of ideas out on the table and figure out which one works best. And another great thing that you should do is form prototyping teams based on who proposed the idea. So if a student proposes a catapult, you don't want to stick them on the wheeled shooter design, because often students have a lot more passion for the design they proposed. So next you want to build a prototype and test it, and we're going to talk about building techniques later. So once you build your prototype, you really need to focus on collecting data. This is the most important part. It's a big part of the engineering method. It's a big part of the scientific method. And when you do this, you want to focus on one variable at a time. So this is called the independent variable. So what this means is that when you're building your mechanism or when you're building your prototype, you really only want to change one thing at a time and see how that affects the system. So let's say you're building a claw. You don't want to change the position your servo goes to and the gripper material on your claw each time. You might just want to change either the servo position or the gripper material, and this can really help you narrow down exactly what is having an effect and what is having a positive or negative effect on the design. If you have multiple things going on at once, you'll never be able to figure out what really worked and what was just a lucky combination. You also want to do quantitative observations. So quantitative means numbers, really solid numbers. So you may have speed. So speed, how fast can I extend my linear slide? How fast can I shoot 3 balls? Then you may have percentage scored. So if this is a shooting game with the target, can I get 80% accuracy? Can I get 70% accuracy at different distances? At 3 feet away, what's my accuracy? At 4 feet away, what's my accuracy? Because then you can use those to quantitatively evaluate your mechanisms and then figure out which one was actually best. We also want qualitative observations. And a lot of times this can be, you can take a video and look at that later and then write down some qualitative observations, because this high-speed video, especially with modern smartphones, is so easy to take. You can spot things you may not notice before. So qualitative observations, and this high-speed video can also be used for speed and things like that. You can put a ruler behind your mechanism, then track the object with that video and see how many frames it takes for that object to move across the screen, and then based on that you can figure out how fast your object's going. But these qualitative observations of prototypes might be ease of building and success. So let's say you have a really complicated mechanism. You can write that in your notes that this is really complex. I don't think we'll be able to build it successfully. And this really depends on your team, not other teams. So you might see team 11115 gluten-free building this really complicated virtual 4-bar system to lift these stones up 15 or 13 to 15 bricks high, but your team may only be able to have the skills to go 4 high. So you really want to evaluate this before you go into the next step. You also want to figure out the general size of that prototype. Like here you can see this prototype can go pretty high, and this lifting mechanism only sticks out in front of the robot, so that might be an advantage, but maybe a disadvantage is that it's wobbly. You also want the ability to work with other designs, so you want a way to interact with this design. So one example I can think of is on our FRC robot. I also do FRC with Cupertino High School and FTC as a community team. But one thing we focused on was our shooter. We had to get balls from the ground into our shooter. But if we wanted to build a really good shooter, we ran into issues where we were not able to actually get that ball into the shooter without having the ball get ripped to shreds. So you really want to concentrate on how easy is that prototype to integrate with other prototypes or other parts of your robot. And you also want to figure out how hard the software is for your design. You really don't want to design something that will take a really complex software system to solve or to run effectively. So an example of this is arms. You don't really want to run a robotic arm with 5 different stages, because the control for that arm is just going to be really hard for your programmers and just take too long. So then as you build these prototypes, you want to start narrowing down prototypes and making them better. You want to pick the prototype that's starting to perform better, and then you want to really start narrowing those down and fine-tuning the prototypes. And you should give yourself more specific criteria. And you kind of want to make these hard. So you don't want these to be easy to achieve, because then every single prototype you build gets through. But you don't want these to be so hard that you're still prototyping by the time your first competition arrives. So with an intake, some more specific criteria might be the speed of the intake. It might be how well it responds to off-center alignment. How well does it stall? If a stone gets in there, does it actually have the torque to suck that cube in? If it gets obstructed by the mats or something. Depositor might be the speed or the motion path of that mechanism, or how repeatable it is. So if you drop the stone with your depositor 3 out of 10 times, is that really worth it? Or do you want to go for maybe something that's slightly slower, but only drops it maybe 5% of the time? So once you do this, you really want to determine what variables influence your mechanism. Once you figure out your mechanism is doing really good, or it's your prototype's being successful, you want to figure out what actually matters about your mechanism. So since a lot of people are predicting that this is going to be a shooting game, let's just assume we're going to be using a wheeled shooter, and you guys decided on a wheeled shooter for your prototype. So what might matter is wheel material, your wheel speed, your gripper material, your sizes of everything, the compliance in the mechanism, the spacing between maybe the wheel and the backboard, or how many wheels you have. And you really want to figure out if any of these really matter, and figure out the their accurate positions of each of these. You want to know, going into designing your mechanism, you want to know that I'm picking a 35 durometer Andy Mark wheel, or I'm picking a 90 durometer Andy Mark compliant wheel, instead of going into your final design and not really knowing what size wheel or how fat or how big it is. And you also want to figure out the wheel speed or things that are limited by your motors. You don't want to build some massive prototype that really needs you to spin up your wheel to like 5,000 RPM or 10,000 RPM and then find out your motors can't handle that. You also want to eliminate confounding variables within your mechanism. So one thing a lot of rookie teams make a mistake with, or a lot of even experienced teams make a mistake with, is when they build a prototype, they often test it with their hands. So this is something our Cupertino High School mentor taught me, Charles Williams. He taught our team that we should always run a prototype without our hands as much as possible. You don't want to be holding the prototype and controlling it. So an example of this would be an intake. You don't really want to be holding two sets of compliant wheels on motors, because just unconsciously you're going to start adjusting things to make it better to suck in these cubes, whereas in reality, if your motors are hard mounted, there's nothing that's going to be constantly adjusted. So you want to get hands-free operation as much as you can. So one thing that might be an example of this is you build a test chassis, or not even a test chassis, you just put your robot on something that can slide around, and then you can push the back of that test chassis instead of holding the mechanism itself. And this way you kind of know how it'll react on a real robot with human drivers. And you also want to test in a competition environment, so mats. One example that I saw of this is that a team had a polycarbonate ramp for their stones this year. So they would intake them, they would slide up a polycarbonate ramp. That polycarb ramp was really close to the ground, and I guess their mats were super new at home and super flat, because when they showed up at competition, when the field wasn't exactly perfect, that polycarb would clip on the edge of a mat that was slightly sticking up and make this loud sound. It'd snap up, and by the end of competition, it's damaging the polycarb. It's kind of messing up the field. The refs might not be happy. So you really want to figure out what things might happen in your competition environment. And another thing is mats. If they're small tolerances or big issues, or if you need these small tolerances, you should get new mats to practice. So this is more for advanced teams using odometry or things that really depend on the quality of your mats. So you need to figure out, is my odometry not working well because of the mats being bad, or is it because my odometry modules are actually pretty bad? If you don't know what odometry is, don't worry about that. I'll give some more resources at the end of this presentation where you can look into that more. So now we really need to come to a consensus. So based on data, you want to pick the best design possible. And coming to a consensus means that you're not voting on a design. You're not having half of the team or 2/3 of the team say, I want to use this design, and then the rest of the people are sent out of the room sulking because their design wasn't picked. You want everyone to work together, everyone to agree on a single design or a single prototype that worked effectively. So when you go into the season, everyone's on the same page and everyone understands why you're pursuing that design. You also don't want your design to modify your strategy. So if you said, I want to pick up 6 stones, and you know that's really difficult for your team to build a linear slide mechanism to lift up 6 stones, but you can make it easier by sacrificing your intake, this might affect your strategy, because you might know, oh, I'm not a really good team, my strategy will just be delivering these stones. So then at that point, you really need to think about if it's worth it to sacrifice your intaking ability to stack extra high. So you need to not modify your strategy based on your design. You really need to set your strategy in stone as early as you can. So as I said before, robotics is not a democracy. You don't want to vote on the wants. You want to discuss them together, and then once you agree as a team, you move forward. So there's also some cases to skip prototyping. You only need to prototype things you want to work. This may sound like everything, but really you don't need to prototype a battery mount. You don't really need to prototype a drivetrain. You don't really need to prototype things that you've done in the past by your team. So if your team has experience with linear slides, you might just be able to say, hey, let's just redo what we did 2 years ago, or redo what we did last year. Or if your team can buy a kit, if you can buy it, this is an FRC kit, but if you have an FTC kit, there are a lot of linear slide options that you can just buy off the shelf and assemble the kit according to the instructions. You don't really need to prototype that because you know how it's going to perform off the shelf. But you want to be careful with things that look the same but really aren't. So a lot of times you're going to be dealing with things that may seem the same but actually perform very differently. In FTC right now, I can't think of specific examples, but in FRC, one example might be foam balls. Each year, although you might be shooting, or every couple of years you're shooting foam balls, but every couple of years that foam changes a lot. So previously, the foam might have been smoother, might have been less grippy, and this can really change how your design is impacted. And this is really when you know you can design something well. So if you know you can design a linear slide mechanism well, or you can design a vertical 4-bar well, you don't really need to prototype these things. So there's this trade-off. Should I prototype more and iterate those prototypes, or should I really quickly build a robot and just iterate the heck out of that robot? So what you want to do is decide that on things that are adjustable and save those for later. So some examples might be intake speed. Some examples might be your hood angle, because you may just be able to tilt your hood on the final design. But you really want to prototype things that won't be adjustable later on, that compromise a big part of your mechanism design. So one example of this might be vertical 4-bar versus horizontal linear slides for a skystone robot to move those stones outside of your robot. Since this is a pretty big part of your robot, you really want to prototype or design something early on, so later in the season you're not blindsided when it doesn't work, or it's not as effective as you thought it would be. So now we're going to be talking about prototyping specific robot parts. This is going to be including mechanisms and drivetrains and things. So let's start with your drivetrain. Your drivetrain shouldn't change too much after it's picked. You really want to set this in stone early on, and you don't want to really ever change this unless you have time to make a really big redesign. So you also want to decide on a style early. I would recommend Mecanum or Tank, and I'll give some resources on how to pick the best Mecanum wheels or how to design a tank drive at the end of this presentation. But you really want to design something that you know works well. You don't want to try new things like a butterfly drive or a swerve drive during the season. The time has passed. You have to do these in the off season, because you just will spend a lot of time wasting when you know that these are solutions that work. And you want to evaluate the pros and cons. So even though I highlighted Mecanum and Tank, you want to evaluate the pros and cons of each of them. So maybe one case in Mecanum is that you can strafe really easily. So when you're stacking those stones in Skystone, it may be hard to move left and right to align stones on the foundation if you don't have a Mecanum chassis. If you have a Tank chassis, it'll be pretty difficult. But you can maybe design around this. Like one of the most successful teams this season was Team Data Force. They had a tank drive, but they also had this massive turret on their robot, so they could control the position of the cubes a lot more finely than you would otherwise be able to do. So then once you decide on your drivetrain, you have benefits between kit drivetrains and custom drivetrains, including cost, your time, things like this. So cost really depends on your team. Our team has a CNC sponsor. One of our team students, their parents manages a machine shop, so we get free machining, so it's cheaper for us to do a custom chassis. But for a lot of teams, it's cheaper if they don't have the sponsor support to do a kit chassis. You also have time considerations. For our team, we built a custom chassis last year. We have experience with custom chassis. We've CAD'd a couple of custom chassis over summer, so we know this. We can build this really quickly. You don't have to worry about it too much. But if your team is starting fresh, or you don't really have the experience, you want to just maybe design a kit chassis. You also have customizability. Both kit and custom offer pros and cons. There's some ways to get around this I'll talk about later, but with kit, you can often mount things in different ways. Depending on the kit, like red extrusion, you can slide things around. With GoBuilda, you have a lot of hole options. You also have size constraints. Maybe you're generally finding that your kit parts are too big. Like I know GoBuilda has some pretty solid channel, so it's pretty big. You might find it too big for your needs. You might want to just build something custom or choose a different build system. So then you also want to focus on what skills, like driver controlling skills, software skills your team has. And you really want to do this cost-benefit analysis, in which case can something really outperform the other if you put in that extra effort. You need to figure out if it's really worth that extra effort. So our team timeline is having a chassis either day 2 or at least week 1. This year we're having issues with shipping parts, so it may take a week or 2, but we're ready to decide our chassis day 1 and have a CAD model ready out the door day 1 or day 2. So these are some examples of the chassis I talked about. These two are custom designs. This is a kit design. So this is a parallel plate design with mechanism wheels. This is a tank drive with parallel plate design. This is a kit drive with tank drive that's made out of kit. So this is GoBuilda. I would recommend GoBuilda if you're pursuing a build system. It's pretty robust. GoBuilda or Rev if you're on a budget, or Rev if you if you're not that great with aligning things precisely, or you really want to have a bit more flexibility. I would not recommend Tetrix. Tetrix has a lot of issues with the build system that really make it hard to get good things working out of it. Another alternative to GoBuilda is Actobotics, which is Imperial. GoBuilda is metric. Actobotics is Imperial. So now let's talk about mechanism design and implementation and prototype. So there are two types of prototyping when you're designing a mechanism. There's the concept selection. So this is the best type of mechanism. So this is maybe a claw intake, or this is a wheeled compliant wheel intake. Then you have parameter evaluation, which is where you decide the best way to build a mechanism. So you want to figure out is it better to build with softer wheels? Is it better to build with harder wheels? What materials can I build with? So even if the way you build your robot changes drastically each season and these concepts change, your parameter evaluation is generally going to be the same. You're generally going to be changing very similar things from season to season. So it can help to contact other teams or talk to other teams to figure out what they've done in the past, or look at other resources, which again I'll have at the end. So what mindset do you need when prototyping? You want to be adaptable, so you want your mechanism to easily be changed on the fly. You don't want to set something in stone and then not be able to change that. And you want your mechanism to be effective, but so you can't be too cheap or too fast. There's kind of this triangle where it's effectiveness, cheapness, fastness. You can only have two of them at the same time, so you can be effective and fast but not cheap. We're not really considering price here, but we're considering kind of your time or energy. So you don't want to spend too little time, and you don't want to go too fast, but you don't want to spend too much time. And you also need to have a strategic mindset. You always need to be thinking about your strategy and the list of wants you decided on at the beginning of the season while you're prototyping. So on adaptability, so prototypes should allow you to modify parameters to change how the mechanism works really easily. So you can maybe adjust the wheel spacing or the type of wheel or the size of wheel really easily. And parameters determined with prototypes should be easily transferable to your final design. So everything should be measured out. So if you finally decide that a wheel spacing of 3 inches is possible on your prototype, or works really well on your prototype, you have to be able to transfer that to your final design really easily. You don't want to go to your final design and find out that, oh yeah, I only have 2.5 inches. So you need to keep track of everything. And you also want to figure out what parameters matter and what don't. So there are a lot of things that on your robot, there are multiple ways to do something. There are multiple ways to really build an effective robot. So you don't want to get stuck on one thing that you're iterating and it doesn't really matter that you should improve it. It's not really the limiting factor in your robot. One example of this might be your intake and depositing speed. So maybe even if you can really intake a cube instantly and deposit it instantly, your driving speed is going to be the eventual, this would be during autonomous mostly. You may be able to build a robot that can go fast enough to pick up 6 stones and deposit them on the foundation, but your programming team isn't good enough, so there's not really a point in building your robot to do those 6 stones. You kind of need to figure out what you need to focus on during the season. So your final design, once you build your prototype, your robot should really exhibit the classic ideal, touch it, own it, which means that the moment you touch a game element, you're in full control. So this means throughout the path of the robot, there's never really any dead time where the mechanism, where the game element is just flying around in your robot, and you want to minimize time losses. So if you look at the top teams, there should be an extra 1 here, but this is Team Gluten Free, one of the best teams in the world. You really want to minimize the time losses between mechanisms. So after you build those prototypes, you want to see how long it takes to transfer mechanisms in and out of the prototype, and use that to evaluate your prototype. You also want to make sure it fits your constraints and meets specifications. You want to make sure it matches those season strategy wants, and you also want it to fit the constraints you decide at the beginning of the season. So now let's get into building prototypes and what techniques you can use. So when you're building prototypes, you want to spend time on key details, but take shortcuts when you can. So this means you can take shortcuts maybe by using clamps instead of screws, or just bolting something together tightly, or not tightening everything down fully, or things like that. But you want to make sure that things are rigid and strong, and you want to make sure that you really spend time on what matters. So then you also want to use simple materials and tools that allow you to make quick changes and do quick tests. So an example of this is you don't really want to end up having to CNC something 10 times to build a prototype, because that can eat away time really quickly. You maybe want to do something where you can use hand tools and cut something yourself in 2 seconds without any CAD. Or you might want to use extrusion when you can slide stuff around, or kit parts where you can try different holds. So when you're testing your prototypes and building them, you can start out with using drills first, and then going to motors and test the this is a pretty fast way of doing things. It takes a long time to get your software team running, or getting some software on your computer to control the motors, so it's often faster just to stick a drill on it and then use that to tune your motors, or use that to figure out how your motors will actually perform. And then later on, once you've refined your mechanism more, you can put an actual motor on there and see if it has enough torque or if it stalls. Then you also probably want to use chain instead of belt or gears. Chain allows you to change the gear ratio really quickly, or the reduction ratio really quickly between different things, and it allows you to change the distances of things and maybe add a tensioner or a sprocket as an idler, just to kind of change the geometry of your design really easily compared to gears or belt. So for this, I recommend getting a chain tool or getting some master links so you can easily change the length of your chain. Then we're also going to talk about 3D printing. So 3D printing, I'm going to go into more detail later, but it's a way for you to pretty cheaply make prototypes of designs or test different things really quickly, or overnight print out 5 different designs, test them all the next day. So I think 3D printing is one of the most valuable things an FTC team can have, especially if you have limited resources, because with a cheap 3D printer, you can pretty much do almost anything you want. So let's start out with using wood within a prototyping context. So working with wood is useful for teams that use a lot of custom parts, because it's pretty similar to cutting out a sheet of HDPE with a CNC, or cutting it out on a bandsaw, or using a CNC to cut out aluminum. So teams should be careful handling power tools and comfortable, so you don't want really young kids working on this if you haven't had the experience or the guidance of a mentor, especially now that maybe the mentor can't be supervising everyone. So these are some helpful tools you can use. So a step drill bit is a drill bit that allows you to drill different sizes of holes. So you can just drill a 14 millimeter bit, slip in a go build a bearing, and test go build a parts you have. Or maybe you're testing with some rev stuff, you can just use the step drill to drill a 9 millimeter hole, put in a rev bushing, and get stuff really easy. And then you can also just drill a bunch of holes in the wood without worrying too much about the cost. You also want to maybe use a scroll saw or a jigsaw or a bandsaw to cut out some weird shapes that would be difficult to cut out otherwise. So you don't want to just want to cut straight lines, you may want to do curves and things. So with some cheap wood, you can pretty easily try different shapes. You also want to use a drill and wood screws, and maybe an impact gun. An impact gun can really increase the speed at which it takes to put together prototypes. This may be overkill depending on the size of wood you're using, but it can really help. And sometimes you just need a clamp. You don't really need screws to hold something together. I remember our FRC prototype was clamped together for a pretty large part of the season, or not a pretty large part, but a pretty significant part of the season, because we just really didn't need to add screws or anything until we moved on to a better design or a more final design. So how do you use wood? You should start out by marking these hole positions for your motion components. So you want to drill slightly oversized holes so there's a bit of slop in your design, so you don't have shaft spining and things, because this is really a prototype. The fit doesn't have to be perfect, and if it only works when the fit is perfect, you're doing something wrong. You want to be able to have a little bit of play in your mechanism, so when you transfer it over to a final design, you have a little bit of room for some changes or some errors in translating it. You then want to cut your outline out and assemble the components. Then you want to just pop in your bearings, maybe press them in, constrain them with just spacers or something, maybe a few shaft collars, and run your mechanism with a drill or motor. So these are some examples in FRC. I wasn't able to find too many FTC examples, but as you can see, a lot of these are basic prototypes. This was probably cut with the CNC or maybe a laser cutter, I can't really tell. So this is more refined, but this is probably pretty simple. You could cut all these edges with a bandsaw. It's 2x4s. It's they just drilled holes here, stuck in some bearings, and used some pre-made rollers or some zip tied together rollers. Or over here, they could test their intake angle or different things really easily. Here you can see the clamps holding the whole mechanism together, so they can maybe change stuff. Yes, and here you can see that they have this mounted on a chassis, so they can push around the chassis and see if game elements are really sucked into their chassis properly. So now let's talk about kit prototyping. So kit is not like pre-built kits, it's like build systems you can buy, like Rev Robotics kits, GoBuilda, Actobotics, and Tetrix. Again, I wouldn't really recommend Tetrix, but if you have a lot on it, it can help. So how should you prototype with kit parts, and what are the advantages? So there's a lot of versatility. All you need is a few screws and connectors, right? Everything's there in the kit. If you have enough screws, you can put together a lot of different things. And so you have Rev, GoBuilda, Tetrix, Actobotics, and these all have different units. Tetrix is a combination of imperial and metric, which makes it pretty weird. But Rev is M3, 3mm bolts. GoBuilda is M4, 4mm bolts. Actobotics is imperial. I think it's 632, but it's a pretty common hold size. So depending on what your team has on hand, you might pick a build system or might order more parts that suit you. Also, a lot of them have linear slide systems and kits already built. So I remember in Rover Ruckus, a lot of teams, instead of building their own custom hang system to hang off of the lander, they just bought a lead screw kit from Actobotics or GoBuilda and then ran with that the entire season, and that was really effective. So how do you prototype with kit parts? You want to have some significant or usable parts that allow you to really easily put things together. So extrusion, in FTC extrusion, you're probably going to end up using most is Rev extrusion. You may use some GoBuilda extrusion, but GoBuilda is more of a channel-based system. You have T screws or hex head screws, and the best thing about this is that you can slide things anywhere on your robot. So this is a robot in 3 days. It was probably pretty easy for them to adjust stuff because they could just slide things around. So then you also have your channel-based systems. So you have Rev, GoBuilda, Tetrix are the most notable. Also Actobotics. So Rev recently came out with a new channel system this year, so I would look into that. It seems pretty promising, but I personally don't have experience with it. So with channels, there are sets of holes along the sides, on the tops, and in different areas, so you could just adjust the mounting and shift things around. And you want to, again, be careful when you're ordering things from different vendors. You don't want to order things that aren't really compatible. Generally, you can stick within the build systems. I think GoBuilda and Tetrix have some interplay, or Tetrix and Actobotics, or maybe GoBuilda and Rev, but usually it's easier to just stick with something and work with that. So now let's talk about one of the most powerful things in FTC, 3D printing. So 3D printing allows you to design these really versatile parts that are beyond kit parts, and it's a lot faster and cheaper than metal CNC parts. A lot of teams don't have access to CNCs or metal or free materials, and a good portion of our parts and many other FTC teams rely on 3D printing. So an example is our depositor. It was 3D printed. It's a pretty wonky shape. It includes servo mounts and everything in one part. So building this with kit parts or CNCing this might be pretty difficult. It allows you to also build things that are really light. So we had these intake arms on a robot that were very light. They could, and we 3D printed those. We went through a couple of iterations to change the length and change the spring angle. So that was really easy to do. We did this kind of rear design part for our servo mount. So these are all things that are kind of difficult to build with other techniques. So 3D printing is a great thing here. You can also save money. So these pulleys, a lot of teams, FTC teams, do 3D printed pulleys. We did 3D printed pulleys on our linear slide mechanism. We used belt, so we used toothed pulleys on there. You can also use them on their drivetrain. Generally, they're pretty strong. You don't have to worry about 3D printed pulleys breaking as long as you set your 3D printer settings right. So 3D printing is kind of the last thing you want to do when it comes to the like your prototyping stage. 3D printing requires you to make a CAD model. It can take some time to 3D print something. It may be faster than other methods, but of course 3D printing does take a pretty long time. So this is kind of in your final stages of prototyping when you really want to get something close, or maybe you want to test some weird geometry that you really can't get with the parts you have. So as I said before, it's relatively cheap and quick. You can do these complex things. You can run your 3D printer remotely with the Raspberry Pi or something, so you don't need to be in your machine shop or have access every day. It's a pretty low learning curve for CAD and slicers. Now there's so many different CAD tutorials out there by other FTC teams and by our FTC team that learning CAD isn't as difficult as it was in previous years. And there are also slicers, which are really intuitive to use now. So slicers are the way you turn a CAD model into something your 3D printer can understand. So you also have issues with rigidity and strength. So obviously it's plastic. There's some weird physical properties of 3D printed parts due to the way they're made. So they're weaker than traditionally made plastic injection molded parts. So you need to consider those. Some will dissolve in water or get damaged by water. Some can get damaged in the sun. Some can melt. A lot of teams have built parts with PLA, which has a relatively low melting point. They leave their robot in a car overnight, or during competition, they leave it in the car heats up, and the robot starts drooping and kind of getting really soft, and then stuff just breaks, and that's catastrophic because you can't really replace those parts quickly. So you need to consider those things. You need to keep your robot safe, and all the plastic parts that are more delicate than the metal parts on your robot safe. It's also maybe difficult, or sometimes there's a issue with not setting up your part properly. You may end up wasting plastic, but this can be pretty easily alleviated with some good training. So these are our recommendations for 3D printers and slicers. So the Ender 3 V2 and the Prusa i3 Mark 3S. So the Ender 3 V2 is about $200. There are occasional discounts or things, but this is kind of your best bet if you want a budget 3D printer. There's a lot of support around it. It's really great for teams that don't have enough money to buy a more expensive 3D printer. But there may be some tweaking involved. Personally, I didn't have any issues with it, but some other people said they had to do some calibration and stuff. So if you don't really have the time to spend on that, or you don't really think you have the skills to spend on that, but you have the money, I would get a Prusa i3 Mark 3S. This is, I think, $900. It's basically the best value for money 3D printer you can get. It's tuned, or best value for money high-end kind of printer. So in FTC, you don't really need the super high accuracy or super high precision you'll get over an Ender 3 from a Prusa i3, but tuning it's tuned straight out of the box, so you can just plug and play. You won't have to worry about any issues. For slicers, which is, again, as I said, something to turn your CAD model into a final thing your 3D printer can understand and use. You can use Prusa Slicer and Cura. These are pretty well supported. They have a lot of people who know how to use them, so it's easy to get help. So now you want to test the prototype. You want to go from a process or software that will allow you to easily test your prototypes. So as I said before, you want to use drills and motors to test your prototype. Drills first, then motors. You don't want to start out writing code for your software. One way to get around the code issue is using this thing called the RevHub interface. So this allows you to read sensors, control motors, move servos without actually having to write any software. You just have to plug your Rev expansion hub into a computer. So this is really valuable. It can save a lot of time. Another thing you might want to use is get a power supply to test your mechanism, so you don't have to constantly charge batteries or wait for batteries to charge if you only have a limited number of batteries. You can just run your robot off of the power supply while you're testing. This is kind of a more detailed thing about the Rev hub interface. So you have things like servo motors, sensors. You can control these, you can read the values of things. So it allows you to really test things, test not just motors and servos, but also sensors, and calibrate your sensors and stuff like that. So once you spend a lot of time on a prototype, how do you get that prototype into a final design? So you want to identify the significant components of your prototype. As I said before, you want to figure out what variables are really essential to keeping your prototype working when it's a final design. So an intake, these things you might want to write down and more. You might want to write down your wheel distances, types, motor speeds, and configurations of wheels, like the shape of wheels, the exact position of those wheels, because you may run into issues where you have jams later on and you're like, why did my prototype work? And it's because your wheels are spaced an inch or two, or maybe even half an inch apart. And you want to have these observations that are kind of harder to record. So if you have something that flexes on a spring, you might want to say, cover a distance of at least 5 inches of travel in that intake. You might want to say, I used this type of spring, pull this hard, so there's this amount of tension on that spring. Also things like you found the initial distance between wheels to work was 4 inches with this type of rubber, but maybe at 3 inches you could use a softer compliant wheel. So maybe in your final design, if you have to make that compromise to use a slightly less better design, you have the data from all your previous mechanisms to say, okay, a 3-inch spacing with a 35A durometer wheel will also work. You also want to figure out your manipulator, make sure it's working properly. You want to figure out if what you built it for is actually achievable. If your prototype could stack 10 high, but your robot can't drive fast enough to stack 10 high, then you don't really need to carry that over into your final design. You also have to consider things like friction in the right place and experimenting. So one example of this that we faced, we had a lot of difficulty with this, was in our prototype we had a servo gripper, and it could grip these stones in a way that really held them tight. But when we transitioned to our final prototype, we had big issues holding these stones, and we realized we adjusted the position of the servo, and this changed how much force and what direction the force was on the stone, and it really changed how our mechanism worked. So you kind of want to figure out, is your force and friction in the right place, and what materials work well. So here, this is some specific information you might record. I'm just going to wait for that black thing to go away. So the arm needs to close at a specific point. Maybe there's something in the game element that you can grip onto more hard, so you need to grab in that specific point. In your prototype, you realize you might have stuff interfering if your arm gets too wide or something. So those are all things you need to carry over and remember. So that's why I emphasize the data acquisition part of prototyping. So now you can have CAD. So free building teams exist, of course, where you just put together a robot and hope it works. A lot of successful teams have done this, but this year I don't really think is a super viable strategy, because you're going to be working virtually. You won't have as much time to try things in person. It may be difficult. So you want to use computer-aided design. So in the early stages, you want to do this thing called cartoon CAD. So after you prototype, you want to box out an area or location of the mechanism. So if your prototype, you determine that it takes 5 inches by 3 inches by 10 inches for a certain mechanism, you can just draw a big box on your CAD model and say, this is for that mechanism, don't interfere with me when I CAD this. And that way, you're not having, when multiple people CAD something, it all works together. It also can help with your space management, just to see how things fit together, and if there's any place you can sneak something in. So once you have your final CAD, you need to figure out how you're going to manufacture all the parts, and you really need to make sure everything's good before you machine stuff, especially depending on the constraints of your team. So our team has a turnaround time for CNC parts of a week, maybe even 2 weeks sometimes. This can be, this means we really have to check stuff to make sure it's right before we send it out. And you also need to remember that small and seemingly design insignificant details can be really significant in the end. As I said before, some things can seem like it won't really have a big impact, and then you build your mechanism and realize they have a big impact. So if you can't measure something on your prototype, you want to make it adjustable in the final design. So techniques for virtual prototyping. Oh, I kind of talked about that earlier. I think maybe at this stage, you should have this discussion with your team right now. If you're watching this in the first few weeks of kickoff, have a discussion with your team how you're going to virtually prototype, how you're going to start your season virtually if you haven't already done so. These are some resources. This is a 3D printing slideshow our team made. This is our team email address. You can contact us with any offers. This is a link to the FTC Discord, which is a way to communicate. There are over 6,000 FTC members on there. So I would really recommend going on there. I'll share this presentation in the description of this video and post these links. There's also this thing called Game Manual 1. Let me just open it up. Sorry, I'll just put it in the description. But there's this thing called Game Manual 1, or sorry, not Game Manual 1, Game Manual 0, which will really allow you to get stuff working and look at other designs and figure out what's successful. It's a really great resource. It's like the Bible of FTC or an encyclopedia. So I'll put that in the description. So thank you for listening to our design. Make sure to contact us if you have any questions at swarmftc. Yeah, we're always open. Our inboxes are always open. And if you see us virtually or maybe at comp in March or February, if possible, maybe say hi to us. And thank you for listening to this presentation, and we hope you guys have a great season. We hope that you have a successful season, whatever success might mean to you.